This is Maple, Math 156, Lesson 3. And today we're going to learn how to do various operations in calculus, taking limits, taking derivatives, taking integrals. So let's just start with limits. So the command for computing a limit is limit. So suppose, for example, we want the limit of the sequence 1 over n as n goes to infinity. Turns out that limit is 0. Now, limit is a command which can also be written with a capital L. So if I write this with a capital L, we don't get the answer, but we get the statement of the problem. This is the limit as n goes to infinity of 1 over n. And again, with all of these Maple commands, you have to look very carefully at the syntax. Limit parenthesis. If I put a space before the parenthesis and after the t, even just one space, I don't get an answer. I get something, it just is repeating what I wrote down. Here, if I put a space, again, it's just repeating, this is an error. It's not giving me the answer. In Maple, when there's a command followed by an argument in parentheses, you cannot have a space before the parenthesis. I remove the space and I get the answer. Here, I remove the space and I get what I'm supposed to get. And what's nice in Maple is you can put these two things together so you get a intelligible human statement. So if I write limit with a capital L of what I want equals limit with a lowercase l, I actually get a statement like this. Let's look at some other examples. The limit of sine of x over x as x goes to 0, you don't write an arrow, you just write x equals 0. This means the limit of x as x goes to 0, sine x over x. So this is an important limit from calculus. You prove that this is equal to, well, let's have Maple do it for us. Oops, you have to put in as x goes to 0 is 1. Very important limit. If I made this the limit of sine of 5 times x over 3 times x, and I have to make that change in both places. It's equal to 5/3. What's another important limit from calculus? It was 1 minus the cosine of x. It's equal to 0. Yeah. This is the syntax for a limit in Maple. There are some typical problems from Math 176. The limit of, for example, t squared minus 9. I want to have that in the numerator, so I need to put parentheses around that. Divided by t plus 3. Oops, that's not good. t minus 3, that's easier. As t approaches 3, you can't just plug in t equals 3 because you would get 0 over 0. But what you learn in Calc 1 is the limit is 6. We took the limit that's over t plus 3 as t goes to negative 3. You get the limit of minus 6. Again, the important thing here is the syntax, how you set up, how you give the command in Maple to compute a limit. Let's look at another one. Suppose we take the limit of e to the x divided by x as x goes to infinity. That goes to infinity. What about x squared? Make the denominator bigger. It also goes to infinity. Let me write these two down separately. And here, this is usually over x. What if you take e to the x over higher and higher powers, like e to the x over x cubed or x fourth? Well, I don't want to have to type this in over and over and over again. So I could make this as a loop. Let's say for n from 1 to 10 do. And what I want to do is compute this limit. I like to indent this a little bit. I'll make this x to the power n. And then my loop has to end with an end do. So it seems like e to the x divided by these first 10 powers of x, numerator and denominator are both going to infinity, but quotient still goes to e to the x is much bigger than x to the n. Suppose I made this even higher. Suppose instead of n, let's make this an exponent maybe 100 times n. So these exponents are, oops, I want this to be 100. 100, 200, 300, up to 1,000. Wow. Yeah. It's still infinity. It's very nice. And this is a nice example of using a limit just to see something that is going on in calculus. Derivatives. Well, we have to know how to define a function in Maple. So if you want the function, for example, f of x equal x squared, that means you want something f, and where if you put in, for example, f of 3, you get 3 squared or 9. So the syntax to define a function is the following. This is really very important. It doesn't matter what name you want to give the function. Let's call it f. So we define something in Maple by colon equal sign. That assigns a value. And if we just wrote x squared, that's not a function. F is just the expression, x squared. If I wrote f of 3, I don't know what that's supposed to mean. It doesn't mean anything. That's not good. The way you define a function of x, whatever your variable is you write x, and then I want x goes to x squared. So you have to put in an arrow. This is really very important. The way you put in an arrow is a minus sign followed by a greater than sign. And in Maple, it comes out looking like this. So this is the function f of x equal x squared. And now if I write f of 3, I get 9. If I write f of 10, well, f of 10, that's 100. That's 10 squared. This is a function. Right? And so you write an arrow in Maple with the minus sign that's the minus sign, followed by the greater than sign. So this sharp sign means this is just text, not a Maple command. You write an arrow in Maple with the minus sign followed by the greater than sign. That's the minus sign. And the greater than sign is that. So that's how I get this arrow here. This is how you define a function. And if you have a function, if I want to plot it, say plot f of x, say x going from -2 to 4. This has to be a lowercase x. Maple is case sensitive. Yeah. That's my graph. That's f of x. I want to solve the equation. F of x equals 196. Solve that equation for x. I get two solutions, 14 and 14. Right? F of 14 is 196. F of minus 14 is also 196. So this syntax is very important. This is a function. And then we need to know how to differentiate. Find the derivative of a function. Well, it's incredibly easy. All you have to know is the first letter of the word derivative. If I write capital D Now, if I already define my function f, that's my function f. If I write capital D of f, I get 2x. That's my function. This is a function. X goes to 2x. So let me recall, what is f of x? X squared. What is d of f? This is the function. What is d of f evaluated at x? 2x. Yeah. If you take the function sine, that's a function in Maple. D of x, the derivative of the sine is the cosine. What's the derivative of the log? Log always means the natural log. Z goes to 1 over z. Yeah. What's the derivative of the exponential function? exp. If I were to write this as so that is the derivative. Now, it doesn't matter what function you take. If I define a more complicated function, let me call it g. So g is the function x goes to, say, x cubed minus 8 times x squared plus 7x minus 100 divided by 2 times x cubed plus x plus 31. That's a function. And if I want to know what is the derivative of that function evaluated at x, well, you just write it like this. One, the derivative of the function is this function. If I want this function evaluated at x, what's that? Yeah. What does this function look like? Well, let's plot it and see. If we plot g of x, yeah, seems to look like this. Here, we have a vertical asymptote. Yeah. What if I take a broader range? Suppose, say, x goes from minus 10 to 20. Yeah. Interesting. Here, there's a vertical asymptote. That's probably because this function isn't defined at some number. This derivative, this new denominator has to be 0 somewhere. Let's find where the denominator is 0. So let's say f solve the equation. Where is this denominator equal to 0? Minus 2.4. That's probably right about where that is. If we were to plot the denominator, let's just take a look at it and see. Okay. It looks like this cubic curve has exactly 1, 0, negative 2.42, right there. And that's why when we plot this function, there's a vertical asymptote at that point. We might ask, what happens to this function as x goes to infinity? Let's see. So we can ask, what is the limit of the function g of x as x goes to infinity? I wrote this with a capital L, so I just got the statement of the problem. I have to write this equals lowercase l. It's equal to a half. So as x goes to infinity, this is approaching a half. What happens as you go to negative infinity? Let's see. That limit's also a half. So this function, as x goes to plus or minus infinity, is approaching a half. Suppose on this graph, I plot not just g of x, but also the horizontal line 1/2. That just means the constant function 1/2. If I want to plot two functions on the same graph, I put the functions inside curly brackets. So this is the line 1/2. You see this function is getting closer and closer to it. Suppose I just restrict the values of y a little bit so it's easier to see what's going on. Maybe y goes from minus 10 to 10. Even minus 20 to 10. Okay. So you can see this function is approaching a half on the left from above and on the right as x goes to infinity from below. Now in calculus, what's very important is to be able to draw the tangent line to a graph at a point. It means the tangent line to the graph of a function. At a point. So, for example, at this function, let's find the tangent line at x equals 5. So, construct the tangent line to the curve y equals g of x at the point x equals 5. So you have to remember from calculus 1 that the tangent line at a point x equals c is given by the following formula. Y equals the derivative g prime at c times x minus c plus the value of the function at c. So again, you're taking math 176. This is from math 175. This you absolutely had to have learned in Calc 1. So let's compute this tangent line. Let me give the tangent line a name. I'll just call it TL for short. So TL is going to be the line G prime at C. So C is equal to 5. So I want the derivative of the function G evaluated at 5 times x minus 5 plus the value of the function at 5. Right? So you know from pre-calculus or high school algebra, this is the derivative of G at 5. This is the equation of the line. The slope is the derivative of G at 5. And at x equals 5, this is the point on the curve. That's the tangent line. So let's go back and plot this. So along with the function, I want to plot this tangent line, which I called capital TL. And look at that. That is beautiful. Right here at x equals 5, this blue line is the tangent line. That's the tangent line at x equals 5. Now, there's a second line that's very important in calculus. It's called the normal line. The normal line at x equals c is the line through the point CG of C, that is the point on the curve, that is perpendicular to the normal line. And you recall from, again, high school algebra or pre-calculus, two lines are perpendicular if the product of their slopes is -1. We call the tangent line has slope derivative of the function at C if this derivative is not 0. Then if it's 0, it's horizontal. If the derivative is not 0, then the normal line has slope. Well, it has to be that the product of the slope of the normal line and the slope of the tangent line equals -1. So if the derivative of, if G prime of C is not 0, then the normal line has slope -1 over G prime of C, the negative reciprocal. Oops, it doesn't look right. Let me do this better. That's right, -1 divided by G prime of C. So how do I get the normal line? If this is the tangent line, And what I will call the normal line, I'll call it L. I'll give it the letters L and L for short. It's the line where the slope is the negative reciprocal of this. That is -1 divided by that slope. That is the normal line. You don't want to work this out by hand. That's why we have maple. And if I go back, and if in this graph I now include the normal line, so I can plot these three together. Fantastic. There it is. Now, it doesn't look perpendicular because it's not drawn to scale. If I want to draw it to scale, I click on the inside, go to scaling constraint, and now it is drawn to scale. Widen this a little bit. So the red is the graph of the function. The green is the tangent line. The blue is the normal line. So this is something you should have done in Math 155. Given a function, learned how to graph the tangent line to the curve at a point and the normal line. Okay. Let's go back to learning how to do derivatives. Suppose we want to define a composite function. So let's see. Suppose I have the function f is x goes to well, x squared. Suppose I define a function h, which is x goes to sine of x. The composite function, let's see, let's try this. F a, curly a, h. Yeah. So this means, this is the notation for, let me just call this G. It's a new G. So f is the function f of x equal x squared. G of x is the function g of x equals sine x. F composed with g, this means f of g of x, the sine of x squared. Composition in the opposite order is a different function. It's sine of the number x squared. This is how you define a composite function. So if you want to take the derivative of f composed with g, let me evaluate it at x, it's easier to see. So you should know from the chain rule, when you differentiate sine of x squared, you get 2 sine x cosine x. If I look at g composed with f, that's a different function. And the derivative of sine of x squared is 2x times the cosine of x squared. And for some reason, Maple writes the x over there, but it's just a funny way to write it, but it still is correct. So this is really quite amazing. It is that if you have a function, all you have to do to differentiate it is use the letter capital D. Where is that? Yeah, D. How to differentiate a function? The function is f of x, d of f. That's it. Now, it is true, sometimes you have an expression. So how do you differentiate an expression? So an expression is something like x squared. X squared is not a function, that is just an expression. And the command to differentiate an expression is diff, lowercase d, the expression x squared, and you have to say what variable you're differentiating with for an expression. This means what is the derivative of x squared with respect to x, and you get 2x. What is the derivative of the sine of x with respect to x? It's the cosine. What is the derivative of 2 to the power x with respect to x? It's log 2 times 2 to the x. What's the derivative of the secant of x with respect to x? Secant times tangent. What's the derivative of arctangent of x with respect to x? 1 over x squared plus 1. What's the derivative of arcsine of x with respect to x? 1 over the square root of 1 minus x squared. Again, for some reason, Maple writes it like this, but it still is correct. So diff is the command for differentiating an expression. Capital D is the command for differentiating a composite function. Now, there's one other thing you learned in Math 175, which is implicit differentiation. Better if I spell it right. So what does this mean? So you might have a curve like x squared plus 4y squared equals 1. So that's an equation, and it's the graph of an ellipse in the plane. At any point on that curve, you have a function defined implicitly, and you want to find the tangent line. You want to find the derivative. So there's a command for doing implicit differentiation in Maple. It is called implicit diff. So if I have this curve, and I want to find the derivative of y with respect to x, why is that giving me that? Yeah, now it works. So the command for implicit differentiation is implicit diff. So here we have a curve, and I want to find the derivative of y with respect to x. Let me just change this a little bit for whatever reason. I'll make this a 20. It's more interesting. Okay. So on this curve, let's see, what is a point on this curve? X equal 4, y equal 1. Let's try. There's a command called substitute. Suppose I substitute x equal 4, y equal to 1 into the expression x squared plus 4y squared equals 20. Ah, so this point 4 comma 1 lies on this curve, which is an ellipse. Suppose I wanted to find the tangent line. Let me call it tangent line at this point. So at the point 4, 1, this is the derivative. Let me add a line. Suppose I want to take this and evaluate that when x is 4 and y is 1. That's this point on the curve. At that point, the derivative is minus 1. So the tangent line will have slope minus 1 times x minus 4 plus 1. So I think that will be the tangent line. Next time, in the next lecture, I will show you a plotting command called implicit plot. I just want to draw the picture now so you can see what's going on. Implicit plot. So I have this curve, and let's say I want to graph it where x goes from minus 5 to 5 and y goes from minus 5 to 5. I'll change that in a moment, but let's just see what happens. Looks like that. Well, that looks like a circle, but it's not a circle. The reason it looks like a circle because 1 unit vertically is much bigger than 1 unit horizontally. To see what it really looks like, I need to go to scaling constraint. There we are. There we are. Beautiful. That's this graph. And on this graph, I want to also graph this tangent line. So if I'm going to plot the two of them together, I have my ellipse and the equation of the tangent line. Well, I should have it in the form y equals. Yeah. Ah, fantastic. So here you can really see what's going on. Here's the ellipse. That's the x squared plus 4y squared equals 20. Here's the point 4, 1, which lies on the curve. And there, miraculously, is the tangent line. Huh. Okay. Well, I'll talk about this kind of graphing capability in the next class. Let's just go back to the beginning and take a look at what we've done in this lesson. So fundamental in calculus is taking a limit. The command is simply limit, but you have to have the syntax right. The function, what you're taking the limit of, and as n goes to what? Infinity, 0, or something else. With a lowercase l, you get the answer. With an uppercase L, you get the statement of the problem. When you put the two together, you get a nice expression that looks like this. That's a limit. There's a loop that just to see what happens with something. Defining a function maple, extremely important. This is the syntax. Differentiating a function is simply the letter uppercase D. when you have an expression, the command to differentiate is diff. This is this @ symbol, which is Shift 4 on your keyboard, is the operator for composing two functions. And knowing about tangent lines and normal lines. So if this were Math 175 and Math 155, you wouldn't have gotten to this yet, but you're in Calc 2, so you know all of the theory behind this. So I will, right, so that's it. That's lesson 3. Just save this, and we are done.